morning, and this is part 2 of our unit on light, and I wanted to go a step further from what we did with part 1 and start talking about the kinds of light that we are supposed to be familiar with and some of the mathematics, the simple mathematics that goes along with it. Okay, so first of all light falls under the category of electromagnetic radiation. And all forms of electromagnetic radiation are considered to be forms of light. Now, right away that kind of throws a wrench in the works because most of the time we think of light as just the kind that we can see. And the kind that we can see makes up just a very, very small portion of what we're actually able to see. So let's look at the different kinds of electromagnetic radiation and then talk about the ones that we can actually see. The electromagnetic spectrum, which is EMR spectrum, includes, it starts over here on this side as radio waves, and then there's a number of different kinds of radio waves which you should be able to be familiar with. And then we've got TV in here, we've got microwaves, like the microwaves that cook our food in the microwave oven, but it also includes the microwaves that send us our cell phone signals. Okay? And then after microwaves, there is IR. IR is abbreviation for infrared. Infrared. Okay? And that's the IR. And then the visible light spectrum is that part which we actually can see. And then after visible, there is UV, which stands for ultraviolet. And then past ultraviolet is X-rays. And out past X-rays is gamma. I hope that that is visible on the screen there from where you're watching this. Now, one of the things that we should recognize about this, first of all, I guess, is the visible light range. Most of us grew up with the idea of Roy G. Biv. These are the visible colors of light that our eye is capable of picking up. And that's red, orange, yellow, green, blue, indigo, violet. Okay? And these are the only ones that we could see, but you can see that there are a number of other forms of electromagnetic radiation that are in continuous exploration or continuous usage in our everyday world, and I would like for you to make sure that you understand some of the basics and facts about these. So first of all, let's talk about wavelength. Okay? So when you look at this spectrum, the wavelengths are longest over here with the radio waves. There are radio waves that are as long as football fields. We'll talk about the mathematics that goes along to figure all that out. But they are longest over here in the radio wave section, and as they come across over here to gamma, they are shortest. The shortest wavelengths are over here on this side. Now, if we talk about frequency, the frequencies are small over here on this side, And as you go across to over here, they are the largest frequencies on this side. So as you go across the chart, they go from small to large. They go from longest to shortest. Now, another characteristic which we should be familiar with is the idea of energy. The amount of energy that the radio waves carries is small. As you go across the chart, the energy of gamma rays is very large. So the amount of energy associated with gamma rays or X-rays, they have enough energy that they go right through you. And so over here on this side, we know that radio waves literally can bounce off of objects, and so they don't have that penetrating ability. And so we're not really seeing a lot of energy associated with those particular waves. What else do we want to see here? First of all, make sure that you have this copied down in your notes so that you understand that the radio waves are the long ones that start over here on this side. They get predominantly shorter as they go across, and so on. Have this written in your notes because I'm going to erase it here in just a second. Now, the next thing that I wanted you to be familiar with, and I think that you will see a similarity to some of that other wave things that we did, was that all the forms of electromagnetic radiation have a specific speed. Electromagnetic radiation has a speed which has been rounded off to 3 times 10 to the 8th meters per second. So 3 times 10 to the 8th meters per second is the speed of light. And the speed of light is often given the abbreviation c. In a very famous equation, we have Albert Einstein says E equals mc squared, where the m stands for mass, the c stands for the speed of light squared. And so the letter c is used for speed. Now, when we look at an equation that you've used before, the speed is equal to the wavelength times the frequency. Okay? And one of the things that we do, or that I've done in physics for years and years, is the idea of radio stations. Okay? And most people don't listen to AM radio station much anymore, but AM radio stations were always broadcast in kilohertz. Okay, and that term hertz should make some sense for us here. And so AM radio stations were in kilohertz. So when I saw, I listened to 750 AM, which happens to be WSB. Okay, that 750 is 750,000 hertz, which is the frequency that the radio station is broadcasting at. So knowing that right there, and not knowing the wavelength, but knowing that the speed is 3 times 10 to the 8th meters per second, you can see how easily we can divide this over to the other side, and we can figure out the actual wavelength of the radio waves that are being produced by WSB. So we take 3 times 10 to the 8th divided by 750,000 equals, and it turns out that the wavelength is going to be 400 meters. Let me double check that again. 3 times 10 to the 8th divided by 750,000 is 400. So the wavelength for the AM radio station is 400 meters. That's approximately 4 football fields long. Okay? Now, let's do another one right quick so you get the hang of it. Suppose that we're talking about FM radio. FM radio is going to be broadcast in megahertz. Prefix mega, as you should remember, stands for the word million. Okay? So let's assume that we listen to 95.5 FM on the radio dial. Okay? Well, 95.5 FM means 95,500,000 hertz. So that's actually 95,500,000 hertz. Got to be in proper units. Okay? And, whoops, excuse me. And the wavelength is what we're looking for. And the speed is still 3 times 10 to the 8th meters per second. Okay, so we solve for wavelength. 3 times 10 to the 8th divided by 95 equals. And the wavelength comes out to 3.14 meters. So the radio station that's broadcasting at 95.5 FM has a wavelength of 3.14 meters. Now, that in itself is relatively simple. Okay? Let's jump into something that's a little more challenging, and it's just a matter of a conversion on your part. Okay? So, I'm going to erase this for just a second. The speed is still equal to the wavelength times the frequency. Okay? Let's switch this up a little bit. And red light, the color red, has a wavelength of 700 nanometers. Okay? A unit that is very common in the study of light. Our issue is that we got to figure out how many nanometers there are in a meter so that we can work in the appropriate units. If the speed is in meters per second, then our wavelengths have to be in meters. And so it looks a little bit like this, and you should remember this from factor label, nanometers, nanometers, here. And then we know that there are 1,000 nanometers in 1 micrometer, and there are 1,000 micros in 1 millimeter, and we know that there are 1,000 millimeters in 1 meter. Now that's a conversion that you should be able to do easily, but let's shortcut this a little bit. This is 10 to the third, this is 10 to the third, this is 10 to the third. So we're taking, and let me write it right here, 7 times 10 to the second nanometers divided by 1 times 10 to the 9th, because there are 10 to the 9th nanometers in 1 meter. And so you've got, this is going to end up being equivalent to 7 times 10 to the minus 7. Because, and put it in your calculator and see, 7e2 divided by 1 times 10 to the 9th equals. And it should come out to 7 times 10 to the minus 7. meters. And so 700 nanometers is going to be equal to 7 times 10 to the minus 7. Now, if we go back over here, and we have 3 times 10 to the 8th meters per second, and we have 7 times 10 to the minus 7 meters for the wavelength, and we're solving for the frequency this time, you've got 3 times 10 to the 8th divided by 7 times 10 to the minus 7 equals, and the frequency comes out to be 4.29 times 10 to the 14th, and that's hertz. Okay, run that on your calculator, make sure you get the same answer that I do. Okay, that the exponent here is negative. But those are some of the simple calculations both for wavelength and frequency, and that's based on the idea that the speed of light is constant. Now, the speed of light changes when it goes into different materials, but as it's traveling through air, the 3 times 10 to the 8th is a rounded off value that is acceptable for all of our calculations we're doing in here. If you have any questions, save them, write them down, and when we have our face-to-face class meeting, make sure that you ask. That's all for today. This is the end of part 2.